Oh my gosh. Yeah.
Okay. So we were looking at drawing trajectories for our solutions. We know how to solve, like for instance, if I was giving you a system, this one's like a really interesting system, a unique system in the sense that they're not coupled, but you could still solve it and you'll get your eigenvalues and eigenvectors. But the idea is, how do you plot these solutions? When you write out the, general solution in vector form and multiply it out, your x solution is this and your y solution is this. And we just said, well, this is just a general solution because the C1 and C2 is still in it. But as long as you put, as soon as you plug in an initial condition, you'll get like some value for C1 and C2, and that'll give you one solution. There's an infinite family of solutions, and your phase portrait would have like an infinite number of curves on it, solution trajectories on it. But if you just want to get a general feel or picture of the solution space, then you want to just choose some few easy trajectories. So I just chose these deliberately to be right on these axes. I just said, okay, well, I want to look at the solution that contains 1, 0, negative 1, 0, 0, 1, and negative 0, negative 1. But there's all this white regions in between these lines in these quadrants that you probably want to draw a solution trajectory in those regions. So because that page is kind of cluttered, I'm going to do a new page. This solution is still the same, so I'll just copy and paste this. But now this is the general solution. We want to actually try some trajectories. Like, let's suppose we say I want to force my initial condition to go through 1, 1. So I can do that by saying that y naught and x naught are both equal to 1. That means that like there should be it's going to be a trajectory that is forced to go through this initial condition. So that means that at t equals 0, x has to equal 1 and y has to equal 1. That's one way to force the trajectory to be drawn in this region. And if you do this, then you plug in x is equal to 1. When t is equal to 0 means e to the t is equal to 0. So that means that e to the 0 is 1. So you get 1. Same idea with this one. C2 would equal these. So then your xy solution for this initial condition would be e to the t and e to the 4t. And if you look at t equals 0, just like we wanted, it's going to be at 1, 1. Because when t is equal to 0, it's e to the 0, which is 1. And then e to the 4t also will become e to the 0, and that's that. Now, if I increase t, how is this parameter? This is a parameterization of the solution curve. How is this going to look when we increase t getting bigger and bigger? That means your x coordinate is growing and your y coordinate is growing. So you might think it's going to be like this, just like a straight line that goes up this way, but one of them is growing faster than the other. E of t, right? And then E of 4t, which one is growing faster as t goes up? 4t is growing faster, right? So it shouldn't, they're not, like they're both E of t, then they're both growing at the same rate, and this arrow will be fine. But you'd want the arrow to kind of go up faster than it's going to the right. So it's going to actually bend kind of like this. So I'll just delete, come on. It's going to bend up like this, kind of, if you get higher. So it's like saying my e to the 4t is going to make the y go bigger than the x. Let's go the other way around. As you go down in t, so if you go negative t, both of these are going to limit to 0, right? Because e to the negative infinity, e to the negative 4 infinity. But one of them is going down to 0 faster than the other. Which one is going down faster? The y one. So that means that I'm going to have to draw a trajectory that's not just straight, but it's going to actually fall faster than it's going to go down. So it's going to be like, okay, what I'll do this, just do this. and I'll just say this is my point. So the idea is that it's going down faster than it is going up. So it's going to bend downwards. Like if they're both going down straight the same rate, then this will be the straight line, right? This will be a straight line like this. But this is showing you that the y is going down faster, so it's dropping faster than it's going to the left. And then the other way is like bending up because you're going up faster and you're going to the right. So that's one trajectory. Let's look at another trajectory where you might say, oh, I'm going to do one down in this quadrant. That means I'm going to say x naught is equal to -1. This is how I can force to draw a trajectory in there. And then y of 0 is equal to 1. If you do this, then your C1 will equal to -1. And your C2 will equal to +1, which means that your xy trajectory will equal e to the -t, and then e to the 4t. When your t is equal to 0, you will be at e to the 0. Sorry, I forgot to put a negative sign. This C1 is a negative, so it's going to be negative e to the t. So when your t is equal to 0, it'll be -1, because e raised to 0 is 1, and then y will be +1. So this will be the point for when you're -1, 1. This is going to be for when t is equal to 0. Now, if you go forward in time, that means you're making your t go to infinity. Your x is going to go further to the left because it's going to be -e to the infinity. So it's going to go towards the left. Your y is the same as last time. It's going to go up. But because it's 4t, e to the 4t rather than e to t, you're going to go up faster than you're going to the left. And then similarly, if you're going making t go to -infinity, they're both going to decay to 0. But so this -e of t will, become negative, smaller number. So it's just going to get towards 0 from the left, right? But this one will also go down just like we had before, but it'll go down faster than it's going to the right. So it's going to basically draw a similar curve, but it's going to look like this. Okay. This is like so basically, it's just going to be a parabola. Let's just do this. So it's going to be like a parabola like this. Now I could do the same thing over, in these regions where I set initial conditions to be like -1, -1, -1, -1, but the same process will show that the solution trajectories in these regions will look like this. So we have a nice picture now. And why am I drawing the arrows to be in the direction I have is because let's look at this purple one. I have to draw the arrow pointing in the positive t direction. So if you're making t go to infinity, both of these x and y coordinates are blowing up. Of course, the y coordinate is blowing up faster. So it's going to be this direction as a positive t direction. And then you can confirm all these. So in the end, you have a picture where we've done eight initial conditions. So we did 4 right here that did all of these. And then we did 4 right here. I just did these 2, but then these 2 are going to be very similar to those. And so you have a total of 8 trajectories, and you'd want to plot them all in one plot. So I did them separately because they didn't have enough space to write stuff here. But really, you should plot them all together in one phase portrait like this. So these are going to be your solution phase portrait or phase plane of your solution to this system of differential equations: dx over dt equals x, dy over dt equals 4y. So if they say draw the phase portrait for the system of differential equations, you would have to solve it, find the eigenvalues, eigenvectors, write out the solutions, and then you'd have to maybe draw like 8 different trajectories to fill out the whole space like this. I mean, you know, you see this orbit was one solution trajectory, but I said like there are these others. So, I mean, the one we just drew doesn't kind of looks like this, but it's like rotated 180 degrees, right? You might have solutions that look like this, you know. So, this is like the process of building it. But I think this is kind of a lot of work to have to like be like, oh, I gotta pick these different initial conditions and analyze like how this thing is gonna evolve. What's the forward time direction for that initial condition curve? And the purple ones are a little more subtle because they are one of them is not zero. So when one of the coordinates was zero, then it's easier. But if they're both not zero, then it's like, okay, one of them is growing faster than the other, so there's gonna have some kind of a bending going on. So it turns out that there is a easier way. This is the same system, and I'm going to, again, just copy the solution that we just had. So I'll just copy this, and I'm not even going to copy that part. I'm just going to copy the part where it just gives me the eigenvalues and eigenvectors. So when you solve this, you found two eigenvalues, and I can write underneath, like for this one, lambda 1 was equal to 1, because e to the t, right? And this one, lambda 2 was equal to 4, because this is 4t. And then what was the eigenvectors that corresponded with those? So for this one, the eigenvectors. For this one, the eigenvector was equal to 1, 0. I'll do C1, 1, 0. And then for this one, the eigenvector was C2, 0, 1. I mean, this is like coming from, you see these vectors right here. Now, there's a way to be able to draw these trajectories just by looking at these eigenvalues and eigenvectors. So what I'm going to do first is notice this is my eigenvector, C110. I'm going to draw the line that this eigenvector represents. That means, suppose you make C1 vary, you know, vary C1 from, I guess, negative infinity to positive infinity. And the 0.10, okay, so there's going to be definitely a 0.10 on it. But then if you make C1 equal to 0, it would be like 0, 0. And then C1 equal to negative 1, it would be negative 1, 0. It's just going to trace this line. What about this one? This one is going to trace this line because it's 0, 1. So it'll trace this line. And here is where I'm going to underline the eigenvectors. And I'm going to point out that these eigenvectors are positive, which means that arrows point out. From the origin. So when these are positive, these are going to point out. It comes from the fact that this is e of t and this is e to 4t. Like when we go up here, this was e to t, e to 4t. And so you know when you're positive time, both of the coordinates are blowing up, so they have to go out. So it's always going to follow that process. So that's going to make the arrows point out. We've done, that's it. So we got 4 trajectories. I mean, this was essentially the same picture that we got up, up here before I drew the purple in there. We got these 4 right here, the blue, the red, the orange, and the green that we had done one by one. We got that all at once by just looking at the eigenvectors, right, plotting that, and then looking at the eigenvalues and getting the arrows correct for that. Okay, so we got that part. Now, the purple ones are a little bit harder, which was the ones that were in these regions right here. So the way you're going to look at that is you're going to take the 2 eigenvalues. You have lambda 1 and lambda 2, right? So I'm going to compare the magnitude of those, which means the absolute value. And if you do, you can see clearly here that in this particular case, lambda 1 is 1 and lambda 2 is 4. So the absolute value of 1 is less than absolute value of 4. you don't even need to take the absolute value because these are positive, but in general, you do need to take the absolute value because they could be negative, and it's really about the magnitude rather than the actual absolute sign, or the size. So when lambda 1 is less than lambda 2, the way that it's going to bend is it's going to become, so you're going to be tangent to the one that has the lower magnitude eigenvalue. So that means you're going to be tangent to eigenvector 1 as you approach the origin. And then you're going to become parallel to the larger eigenvector, the eigenvector with the larger eigenvalue. Going away from the origin. So that means that as you approach the origin, you're going to become parallel. I mean, you're going to be on tangent to the, so let's label, this is the eigenvalue that has 1, and this is the eigenvalue that has 4. So you're going to become tangent to the blue as you approach the origin, and then you come parallel. So this is going to draw a line that looks like this. So this is like you're getting tangent to the blue, and then as you leave, you come parallel to the red. And the arrows will, because both eigenvalues are positive, they will also point out. On this side, same idea. You become tangent to the blue as you approach the origin. So it's going to become tangent to it, and then progressively becomes parallel as you leave the so parallel means that it's just going to be like almost vertical. It approaches vertical as you get further away from the origin, and then it bends into or tangent to the blue. In all of the quadrants, it'll do this. And it's parallel as you leave out. So that's it. You don't, it's consistent with what we saw. So at least so the quote unquote correct way to do it would be like to go and do all these like, oh, I'm going to use these different initial conditions and see what the solution is for that, what the C1 and C2 for those are, and then just like think about what kind of curve that would trace as you make t vary from negative infinity to positive infinity, and it'll trace these curves. But it will always be the same as if you did this, where you just draw the eigenvector directions right away. Like what line do these eigenvectors trace? Putting arrows to be out if the eigenvalues are positive. If they're negative, then everything flips because t is now becoming negative t and negative t, and so forward time and backward time are flipped. And then your purple, the way it bends is going to be depending on the magnitude of your eigenvalue. So it's going to bend towards the eigenvalue with the smaller magnitude and then become parallel as you go out from the origin towards the eigenvalue that has the higher magnitude. Okay, so this is what the summary is. This is what the book has for this problem. They also draw a bunch of direction vectors. That one is basically drawing little ticks that represent dx over dt, dy over dt at each individual point. And the idea is these direction vectors should match the flow of the solution trajectory should match the flow of the direction vectors, meaning that it should be tangent to and in the same direction as the direction field. And there are infinitely many that you could draw in between everywhere, but like this is enough to get an idea for how the solution looks like. And I'll also point out here that the middle right here, since all the trajectories point out, this is an unstable node. Or you could say an unstable equilibrium, but we'll just call it unstable node. The trajectories are tangent to the eigenvector direction corresponding to the smaller absolute value. So that means that these trajectories that are coming in here are tangent to it, and then they become parallel to the trajectory that has the larger eigenvalue as you leave the origin. Okay. All right, so let's do one that we had done before. This one is 4235, I think. We did it back then. This one, we did this one right here. So we got this as the solution right here. This was like back when we were solving this system, -5, -4, 2, and y, and 1. -5, -5, -4, 2, and so this is the same system we had solved back then. I'm not gonna go and try to solve the system over again, but I will, like, let's just write it on the bottom here. The solution that we got for this was vector x of t is equal to c1 e to the negative t -1, 1 plus c2 e to the -3t -2, 1. So that's fine. So this is the same one we had solved back then. The process was to find the eigenvalues and then the eigenvectors, and then you get all this solution. But I'm not interested in doing that over again. I'm more interested in, let's say, how can we plot this? So using the idea that we had before, there's two eigenvalues. There's like the blue one and then the red one. So how do I draw the straight lines? The straight lines are going to come from, so I'll just, note here that I underlined these two in blue and red. Those correspond to eigenvalue 1 is equal to -1, and the eigenvector for that was negative C1, -1, 1. And then the other one is eigenvalue 2 is -3. The eigenvector for that is equal to C2 with a -2, 1. Okay, so we have these two, and you should be able to draw things from it. The eigenvector 1 is -1, 1. Think about what kind of line that would trace if you make C1 vary. You know for sure that when C1 is equal to 1, it's going to be at -1, 1. So it'll go through this point. And then when C1 is equal to 0 goes here. If you make C1 equal to +1, to -1, then it'll be like 1, -1. It'll be here. So it's really just going to draw a line that looks like this. This is your eigenvector 1 direction. Now your eigenvector 2 direction, let's just draw some points. So if you put C2 is equal to 1, it'll be -2, 1, just like here, I guess. And then, of course, C2 equal to 0 will go here. And then C2 equal to -1 will be like +2, 1. So it's just these are going to be the line. This is going to be the line that's going to trace the V2 eigenvector. And the eigenvalues in this case are both negative. Right? So instead of e to the t and e to the 3t, but e to the -t and e to the -3t. So if you go back and look at something like this that we had before, it's as if you had a negative in front of these t's. So that means whenever we had positive time before, it was blowing up. Both coordinates are growing. But if you have negatives in front of these t's and the -4t, then forward time will be shrinking these values. So that means that the arrows should be pointing in instead. So I'll just say these are negatives. Arrows point into origin, which automatically is going to make this a stable node because all the trajectories, this will be not just stable, but asymptotically stable. Let's draw those arrows. Okay, now the purple ones. The purple ones require me to check the eigenvalues. So if you look at the magnitude of the eigenvalue for 1, and then you look at the eigenvalue for the magnitude of the second eigenvalue, this is -1 and this is -3. Yes, -3 is lower than -1, but if you took the absolute value, then this will become 1 and this will become 3. And so really the inequality, this is the relationship. So basically, if you, -1's absolute value is 1, -3's absolute value is 3. So even though -3 is lower than -1, their magnitude is going to have this. So that means that this indicates that you're going to tangent to the blue one, which is the blue eigenvector approaching the origin. Okay. So that means that there's 4 regions that these lines break the plane into. They're not nice, like, equal size, because when we had the eigenvectors last time, they were like 1, 0, and 0, 1. So they split it orthogonally like this. But now we have ones that are -1, 1, -2, 1. It's going to split into 4 regions, but they're not like in this nice symmetric shape. But the idea still holds. There's this big region here, and then there's a small region here, and a big region here, and a small region here. So what if we look at this this small region right here? There's like between this red and this blue. The idea is that as I approach the origin, I have to become tangent to the blue, and then as I leave the origin, I become parallel to the red. So it's going to look like, I'll do this, very obvious. That's good enough. So they're gonna bend in, but if you notice, like I'm making it very obvious that it's like hugging the blue as you get in, and then it's kind of become parallel to the red as you leave out. And then in this region, the same idea, gonna be like hugging the blue, it becomes parallel to the red. That's reasonable. So it's like parallel to the red and then hugs the blue as you get closer to the orange. Now, in these larger regions, you have to still do the same. One approach might be, the idea of as it becoming tangent to the blue as you come in is the same as if you drew it coming out of the origin. It's tangent to the blue, but becomes parallel to the red. So I'm going to be here, and then I'm become tangent to the blue and become parallel to the red. And then you're coming in. So you see, as I leave the origin, I become parallel to the red. As I come into the origin, I become tangent to the blue. As I come into the origin, I become tangent to the blue, parallel to the red. So that's the phase portrait for this system. Okay. Now, let's just say, suppose everything stays the same. You have the same eigenvalues and eigenvectors, but let's say that the bending has to change because suppose your lambda 1 and lambda 2, their magnitude isn't like this, but they're flipped. So instead of lambda 1 being less than lambda 2, the lambda 2 is less than lambda 1. How would that, so what would be the phase portrait if we had the opposite case where the magnitude of lambda 2 is less than lambda 1? I mean, it's going to have a different kind of system, but let's say at the end of the day, everything stays the same, but just this got flipped around where lambda 2 is the smaller magnitude. That means that everything stays the same, but the purple lines will change. So I'm going to just copy and paste. So let's just delete all this purple stuff. So in this case, we're looking at the situation where lambda 2, so that means that this indicates that we're going to be tangent to the red one instead. So last time it was tangent to the blue one, but you see tangent to vector 2 approaching origin. Okay. So in this region, I'm going to just do it in order that we did. In this region, we used to bend towards the blue and then become parallel to the red. It's flipped now. We're going to bend towards the red and become parallel to the blue, which is going to look like. This is, so it's like bending into the red, and then it's tangent to the red and it becomes parallel to the blue. This one is going to be like tangent to the blue. This is fine. So it's like parallel to the blue out here and then becomes tangent to the red. In these regions right here, I'm going to be tangent to the red as I leave and then becomes parallel to the blue. So it'll be like, okay. So that's the solution phase portrait for this case. I want to point out that they look different. If you actually look at these carefully, they are not the same. See how this one's like coming from here, bending in this one? This one's not doing that. It's like coming out from that and comes in from here. And this one's bending into the blue here. This one's bending into the red here. So these are not the same, but they are following the same conceptually idea that you're just going to draw the eigenvector directions. You're going to draw the arrows based on whether your eigenvalues are positive or negative. And then you're going to have the purple arrow ones are going to bend in this very particular way. It's going to depend on the magnitude of the eigenvalues. And the one that's smaller magnitude is the one you're going to be tangent to as you approach the origin. And you're going to be parallel to the larger eigenvalue. And so they're both stable nodes because the arrows are all pointing in, and that's because the eigenvalues are both negative. So how do people feel about that? It's pretty good. Okay. So let's draw one where you may have real but opposite sign eigenvalues. So both of those that we just saw were same sign. The eigenvalues were the same sign. We had like, positive eigenvalues for both, or in this case, negative eigenvalues for both. Those are going to be these kinds of pictures. It's harder. They're harder because they kind of you have to worry about how these purple trajectories, the ones that I draw in purple, how they bend. If you have real and opposite sign eigenvalues, you have something different. So let's go back and review do this by hand again. So when you're trying to compute the eigenvalues for this, it's going to become lambda minus, or I guess it's lambda. It's going to be the same as if you would take the determinant of this. So I'll just do this. 3, 1 minus lambda, which is equal to lambda squared minus 1 minus 3. So the eigenvalues will be equal to 4. Therefore, your lambdas will be plus or minus 2. So you have two eigenvalues, but they're different signs. So then you say, okay, I'm going to find the eigenvalue for when lambda is equal to 2. That's like going back and plotting or plugging into the original eigenvector eigenvalue equation, which is equivalent to, in this case, -1, 3, 1, 1, uv, and then you have 2, uv, and then you can write the two systems. I'm just going to use the first equation because they're going to be the same equation for both. So you can use either of them, and then you'll get that it's negative. sorry, I put a blue line right on top of the negative, but it's really a negative there. So let's say negative u plus 3v is equal to 2u, which means that you can move this u to the other side to be 3v equals 3u, so u is just equal to v. And so you could say one of them is free, so you'll just say v is equal to c1, which means that u has to also equal c1. So your eigenvector will be built off of u and v, and in this case c1 and c1, but you could factor out the c1, and so the eigenvector is 1, 1. And then for the other one, lambda 2 is equal to negative 2. Everything stays the same, so I'll just copy everything. But it's going to be this 2 right here has a negative in the front. It'll be negative 2. And that's going to make this negative 2. Why don't I just use the second equation? So I'll just do the second equation because it doesn't matter which one you use. So I'll do the second equation this time. So if you use the second equation, it's going to be u plus v is equal to negative 2v. And you could move the v to the other side. That's going to make it u is equal to negative 3v. You could say v is free, c2, but that means that u must be negative 3c2. So then your eigenvector will be c2, negative 3c2, which is c2, 1, negative 3. Oh, no, sorry, I flipped it around. U is negative 3c2, and then v is c2. Then you'll get c2, and then it'll be negative 3. Sorry. All right, so those are your eigenvectors. So we're going to do the same thing we did before. We're going to just look at the eigenvalues and eigenvectors and plot those. So I'll just write it down here and say, okay, we had lambda 1 was equal to 2. Lambda 1 was equal to 2, got c1 is 1, 1. So we got that v1 is equal to c1, 1, 1. When lambda 2 is equal to negative 2, your eigenvector was c2, negative 3, 1. So it's going to be c2 and negative 3, 1. This is all you need. I'm just going to underline like this, my blue one. This is my red one. And then we're going to draw, what does 1, 1 trace? That's going to trace this line. It's just going to be a 1, 1 line. This has a positive eigenvalue, so the arrows are going to point out for this. The red one is negative 3, 1. So I'll go all the way down to 3 and 1. So it's going to be like a really flat. Oops. It's going to be a really flat. It's going to be like right here, I guess. Come on. Really flat. 1, 2, 3. So it's going to be like this. And that one's going to this one's going to point in because it's a negative eigenvalue. So we have not both of them pointing in and not both of them pointing out. So what does that mean? Like if we go back up to looking at like this right here, it's like saying one of them is like let's say e to the t, but the other one's like negative e to the negative 4t. So they're not the same sign. The coefficient in front of the t's on both of these are not the same. If they're the same like this, e to the t and e to the 4t, when you move forward in time, they're both blowing up. If they're both negative, then they're both shrinking. But if one of them is positive and one is negative, one of them is blowing up and the other one is shrinking. So if you think about, how if you moved this forward in, let's say if you said e to the t and e to the 4t and you said t go to negative infinity, they'll both decay to the origin and they'll both go into the origin. Or if they're both negative t and this is negative 4t, then when you make t go to infinity, they'll both go into the origin. But in this case, one of them is going into the origin, whereas the other one isn't. So the way it's going to look is as I approach the origin, if I was on this red, I'll go in. But if you're out here, it's like saying, oh, you have basically one of the eigenvalue directions are, so you could say you have the eigenvalues for that one with the eigenvalue -2 is going to have solutions that are going to have e to the -2t. And so if you're out here, you're going to along the direction of red, you're going in, but then along the direction of blue, you're going out. So the trajectories are going to look like this. Only one of them is going to shrink as time goes on, and the other one will go away. So it's going to look like. So, and then they follow the arrows that you have here. So it's going to look like this. This is an unstable node because if you're close to the origin, there are points that will point away, right? So if you're like, if you're right on this blue line, you're getting pulled out. If you're off here, you will also get pulled out because of these purple arrows who are going to pull you out this way. So this is an unstable node, but it is it's a special name. People call this a saddle point, but it's still unstable because there's at least one trajectory that points away. Okay, so those are your real, those are all the real eigenvalue cases, whether they're the same or well, they're distinct, but whether they're the same sign or opposite signs. If they're opposite signs, they'll draw a saddle point. If they are the same, then you're going to have trajectories all going in or out, and you have to think about the bending carefully for that. This one's easier because they just go with the flow of the, so this just like is saying I'm going to get the red is pulling me here, whereas the blue is pulling me out. This one, the red and the blue are both pulling me in, and then it's a matter of figuring out which one is pulling me in faster than the other, and that's why it bends in certain ways. This one, they're opposite, so it's like one's pulling me in, but one's pulling me out, and so you're not going to have trajectories that feed into the origin, just because just like when I was pointing out this solution right here, it's like saying one of them is -t and one of them is -4t. Then as you go forward in time, one of them is shrinking, one of them is blowing up. So you have to, it's not going to both go into the origin. So the other case, the last type, so there's like characteristic equation, you have real distinct eigenvalues. You could have repeated eigenvalues, but I'm going to skip that one, and we're going to look at the complex eigenvalue case. It's no different than what we've done before. So when you have a complex eigenvalue, you can compute the characteristic equation, and you'll just get like -1 minus lambda, -1, 1 minus lambda, and then you can take this determinant, and that'll give you 1 minus lambda squared plus 1 is equal to 0. And if you solve this by moving the 1 to the other side, you'll get this, and then you take the square root of both sides. Take the square root of both sides, you get 1 plus lambda, 1 minus lambda is equal to plus or minus I, and then therefore your lambda is equal to 1 plus or minus I. This is fine. Your characteristic equation is quadratic, so you may end up getting complex. But the only thing you're going to do is you're just going to compute the eigenvalue vectors as usual. So one of them is 1 plus, your eigenvalues will be in conjugate pairs. One of them is with a plus, one's with a minus. So if you did the one with a plus, then you put it into your eigenvalue equation, and you'll end up getting also complex eigenvalue vectors. So your A matrix is 1, -1, 1, 1. You got your UV, and then your eigenvalue is 1 plus lambda, and then you have your UV. And why don't we just use the first equation, because they'll both be equivalent. Then you'll get U minus V is equal to 1 plus I U. You can multiply out the U, and so you'll get U minus V is equal to U plus I U. These U's will cancel because there's U's on both sides. So you'll have V is equal to, what I could do here is I could multiply by I. Let's say I just multiply by I, so it'll be negative IV is equal to I squared U is negative U, because I squared is negative 1. And then if I do that, then I get just that U is equal to IV, because I could just, multiply both sides by negative. So this is saying that V is free, so V can be some arbitrary C1. But if I do say that, then U has to equal IC1. So your eigenvector will become equal to U and V, and so your U is IC1, and your V is C1. You can pull out the C1, and you have I1 is your eigenvector for this one. The eigenvector for the other one, which is going to be 1 minus I, because that's the other eigenvector, eigenvalue, is going to be very similar. It's going to be like, I have no time, but I'll just like write it out. But in the end, you're going to get that V2 for this one will end up becoming equal to negative IC2 and then C2. So then you can factor out the C2, and then it'll be negative I and 1 for that one. But it's really similar. The only thing that changes is this plus becomes a minus. And because this plus right here becomes a minus, because of this eigenvalue, it just changes everything around where this I ends up becoming a negative I. And it's really nice because if you think about it, your eigenvectors are also conjugate pairs. What does it mean to be a conjugate pair? It just means that every time you see I, you just make it negative I. So here was 1 plus I, you just say 1 minus I. Every single time you see I, you make it a negative. That is the same as conjugate. So your eigenvalues occur in conjugate pairs, as well as your eigenvectors occur in conjugate pairs whenever you have an eigenvalue eigenvector equation with complex conjugate roots. This is the proof for showing you that, which I'll talk about next time. This is just saying that your V2, which is your second eigenvector, is always the conjugate of your V1. This little bar means conjugate. And we'll do that. I'll do Euler's equation as I always do. Well, I'll probably abridge it, but basically we want to characterize the real solutions like we always do. And then we'll draw phase portraits for complex, and then we'll move to Laplace transforms, and that's the last topic. So I'll see you guys next week. Yes.